let's next consider how to actually come up with the graph of a quadratic function. And for the moment, we're going to focus on quadratic functions written in standard form, so just written as a polynomial expression all multiplied out. It turns out that this is not at all the best form to have a quadratic function in if we want to graph it. And soon we're going to learn a way to take a quadratic function that's given in standard form and rewrite it in a more useful form. However, for the moment, we're going to just use sheer brute force given a quadratic function in standard form. So here's how we're going to do it. To graph a quadratic function in standard form, we're going to just create an input-output table. So a table showing pairs x and y is f of x. And we're going to show enough pairs that we can see the y values both increase and decrease. Right? In a parabola, either we go up and then go back down, or go down and then go back up. We need to see our y values doing that in order to do our next step, which is to figure out where the vertex is. We hope that somewhere in our table, we're going to have two pairs that have the same y coordinate. The axis of symmetry lies halfway between their x coordinates. Then, if it turns out that our axis of symmetry doesn't have an integer x coordinate, that means that our vertex isn't going to have integer coordinates, so we'll need to figure those out so we can draw them. And then in order to draw our graph, we're going to show the vertex and at least 2 points to each side of the axis of symmetry. And then we'll draw a parabola passing through those points. But we need the vertex so we know how the graph curves. And we need 2 points on either side to guide us to the rest of the shape. Now, in general, it's going to take a certain amount of trial and error to find appropriate x values that are going to let us see the shape of our parabola. So in this next example, we're just kind of going to use brute force. Here we want to sketch the graph of f of x equals x squared minus 4x plus 3. And we have a set of axes where our x-axis goes from -4 up to 4. So we're just going to plug in all of the integers from -4 up to 4 and see what happens. So when x is -4, f of x is -4 squared minus 4 times -4 plus 3. And throwing that into a calculator, we see that that gives us 35. That's not going to be a useful point for our graph, but let's just keep going. When x is -3, we'll have -3 squared minus 4 times -3 plus 3, which works out to 24. Also not useful for the graph we're going to want to draw, but we'll keep going. When x is -2, we'll have -2 squared minus 4 times -2 plus 3, which is 15. When x is -1, we'll have -1 squared minus 4 times -1 plus 3 is 8. Still not useful for the graph we want to draw, but getting closer. When x is 0, we'll have 0 squared minus 4 times 0 plus 3. Oh, well, that's just 0 plus 3 is 3. That's looking better. When x is 1, we'll have 1 squared minus 4 times 1 plus 3. I think that that's 0. Okay, these are turning out to be some nice points. When x is 2, we'll have 2 squared minus 4 times 2 plus 3, which works out to be -1. When x is 3, we'll have 3 squared minus 4 times 3 plus 3. Oh, that's 0 again. When x is 4, we'll have 4 squared minus 4 times 4 plus 3, which works out to 3. Okay, so the points that we found that are going to be nice for the graph we want to draw are these ones here, right? The x-coordinate between 0 and 4. And one of the things we notice is that these 2 points have the same y-coordinate, and these 2 points also have the same y-coordinate. Our vertex is going to be halfway in between there. So according to our table anyway, our axis of symmetry is going to be the line x equals 2. And our vertex is going to be the point 2, comma, negative 1. So to help guide our graph, let's start by sketching the axis of symmetry, right? That's the vertical line x equals 2. So I'm drawing a dashed vertical line, x equals 2. And on that line, I'm going to have the point 2, negative 1. That's going to be my vertex. And then on either side of the vertex, I have 1, 0, and 3, 0. I have 0, 3, and 4, 3. And then any further points from my table are going to extend off the graph, so I can't draw those. And I can just now sketch a parabola that passes through all those points. So when I draw a parabola, I'm going to make sure it's flat at the bottom. All right, I'm not going to draw it pointed at the bottom. And then I'm going to just kind of sketch as smooth as I can, coming up through all of these points. And then beyond my last point, really, I'm almost going to draw a straight line. It keeps curving, but I don't want it to curve back in on itself. And I don't want it to curve further out. And really, by this point, it's pretty close to being a straight line. So the key features, once I have my points, are that my graph is flat at the bottom, and then at the top, it doesn't curve back in. Because if it curves back in, we're no longer looking at the graph of a function, and we're definitely looking at a totally different shape. So as long as it's passing through my points, it's flat at the bottom, and it doesn't curve back in at the top, that's as precise as I need to be in drawing a parabola.